So the problem reads, as shown in the figure above, water is draining from a cone tank with the dimensions provided and into a cylinder tank, and it has dimensions of the tank as well. The depth h is changing at a rate of h minus 12. The volume of a cone is 1/3 pi r squared h. Write an expression for the volume in terms of h. So this is kind of help guiding us our equation. This is telling us to get our equations for h, which means that we want to find a replacement for r. So here we don't have to even make a decision. They're telling us what to which variable to remove and which variable to keep. So we start off with our right triangle diagram. What's the, yeah, 4. Any trouble here? So they're telling us to get in terms of h, which means that we want to find a replacement for r. We want to find a way to replace r. So this is kind of helping to guide us already how we want our equation to look. So now we can put this into our volume equation. Part A is not even asking for the derivative. It's just helping us get it set up so that our volume equation can be ready for the derivative when we get to part B. Okay, we do want to do quite a bit of cleanup here. Let's get rid of the parentheses, the square, what's inside the parentheses. Let's put the coefficients together, fractional coefficients together. Let's merge the variables together as well. And that's all we need to do for part A. So this is only asking us for the expression for the volume, no derivative yet. Huh? Yeah, it's in the numerator. So yeah, I mean we could also write it this way, but I like to write it this way because then we don't have to, that h can just feel like its own thing and the 27 is outside of it. Yeah, but yeah, either is fine, but I like this way more. Okay, part B. Everybody okay with part A? Okay, part B, at what rate is the volume of the water changing? What are we looking for here? Yeah, dV over dt. When h is 3. So now that's kind of helping us to see, okay, we need to build our derivative so that our dV dt will show up. And then we'll do power rule, and then we can start putting information in. Okay, so we're just going to pick up where we left off from part A, build our derivative. Pi over 27, anything happen here? Stays, right? And then h cubed becomes 3 times dh. Yeah, okay. Okay, I'm just going to do a little bit of cleanup, so it just makes it a little bit easier for me to plug in. So we have H is 3. Do we have any information about DHDT?
Yes. The table.
Good. So if we look back at our problem here, it says the depth H is changing at a rate of H minus 12. So they're describing DHDT for us here. So DHDT is equal to H minus 12. Okay, so we can plug everything in, right? We have H is 3, we have DHDT, which we can replace. So now we're just trying to get it down to a number for dVdt. And then once I replace DHDT with H minus 12, I can do a further replacement, replace this H with 3 as well. Okay, what's our unit of measure going to be? Volume is feet cubed per minute. Okay. Does it make sense that we're getting a negative for dVdt?
Yeah.
Okay, because water is draining. Okay, so all right, everybody okay with part B? Part C, let Y be the depth in feet of the water in the cylindrical tank. At what rate is Y changing when H is equal to 3? Indicate the units of measure. So the volume formula for a cylinder is pi r squared H, but then instead of R and H, we're using A and Y just so that we're not duplicating the variables. But if you want to use R and H, you can, but they're specifying Y. So just, well, I think it's best if we just adjust to whatever they're adapting. So let's A is our radius and Y is our height. What's different? How we talked about with cylinders that should make this easier. Radius is what? Constant. So if we can figure out what the radius is, we can just replace radius with a number, and then we can jump directly into the derivative. Okay. All right. So, do they tell us about? Do they give us information about the radius of the tank? They give us the area. Okay, so that's something that could be helpful, right? The area, and what shape is the bottom? Is the bottom of the base there? Circle, right? And what's the area of a circle? Yeah, area is pi r squared. So we can kind of work backwards, right? So they don't tell us radius directly, but we can kind of figure it out on our own here. We know our area is 400 pi. So I'm going to just work on trying to get down to my radius so that I can use it for my equation. So pi r squared is 400 pi, divide both sides by pi. I get that to go away. R squared equals 400. Therefore, my radius is what? 20. So I can just go ahead and replace my A with 20. Sorry, again, A in this case represents the radius. So our A is 20. And we know that the radius is never changing for cylinders, unlike cones. So we can just go ahead and get rid of the A, and that should make our process a lot faster. Mm-hmm.
Isn't pi times 9 greater than negative 9? For B, pi times 3 minus 12.
Oh, yeah, pi times 3 minus 12. So that's 3 minus 12 is negative 9, and negative 9 times pi is just negative 9 pi. What?
Oh, there's a pi there.
Sorry, yeah, negative 9 pi.
Sorry,
Yeah.
that's me.
So as soon as we can find the radius and replace it, then the volume equation is ready for the derivative, right? It's not like cones where we have to go through another similar triangle process. We can jump directly into our derivative step. Okay, so are we okay with this equation getting ready for our derivative? Okay, all right, so V becomes dV over dt. 400 pi y becomes coefficient stays, and then y becomes dy dt. So we would say dh dt, except for the fact that now we just want the height for the cylinder to be a different variable, so that's why they use y, but dy dt. Okay, we're trying to find dy dt. Do we have dv dt for the cylinder? It's related to this, actually. The dv dt for cone is negative 9 pi. What do you think the dv dt for the cylinder is? The 9 pi. So the water that's leaving the cone is the rate that water is entering into the cylinder, but it's going to be positive. Why is it positive? Yeah. So that's the adjustment we have to make, right? It's dv dt is negative for the cone that's losing the water, but then dv dt is positive for the cylinder that's receiving the water. So dv dt is a positive 9 pi. And now we're just one step away to solve for dy dt, divide both sides by 400 pi, and we have our answer. The pi's cancel out, so I'm just left with 9 over 400. What's our unit of measure? Y is one-dimensional, right? This is height, so feet per minute.
So when it gives us that like h equals 3 in the equations, that's just extraneous. That should be unperceived.
Oh, sort of, but then also it tells us that we can reuse this data because it's all at the same moment in time. So that just allows us to reuse. But yeah, we don't necessarily use that h equals 3, except for the fact to pull from part B. Okay, any questions? Yeah.
So it's 8. Or is y
Right, sorry, h, yeah, the h equals 3 is for the h for the cone. Yeah. But the reason that they tell us h equals 3 is so that they can reassure us that we can use the same data from part B because it's the same moment in time. Because if it's a different moment in time, it'll probably be a different rate, and then we can't reuse part B. But they want us to link these two together at the same moment in time.
If it asks,
They'll give us they'll have to give us more data, but typically this. So, by the way, this is an older FRQ. So this actually is this is actual FRQ, and this is kind of like what FRQs do. I mean, you can see that part B is more challenging because there's more steps and it requires the previous step. But you can also see how they kind of help build up the knowledge that you need to get to the next step. So even though it is harder, they do try to connect the parts together so that you're building off the previous. It doesn't always work that way, but this is a good representation of how they like to design for response questions. But it's nice that, early in the year, we're able to kind of see what a full FRQ can look like. Now, having said that, most FRQs that we're going to see are from second semester topics. So we're not going to get a full spectrum of our FRQ practice until we get to second semester. But we're beginning to build that knowledge that we need for second semester, because second semester also, even though FRQs are mostly second semester content, it is building off of first semester content. So it's all connected. Okay, good. Any other questions? Okay, I do want us to return back to related rates, but we have one final topic, and that's L'Hopital's rule. Involves limits. I think you'll find this the easiest of the things that we've done so far. Well, except maybe linear estimation is easier, but this is pretty close. So let's go to page 18. Now, I do want us to revisit limits from unit 1, but just so that we can do it for comparison purposes and how we are able to create these shortcuts that we weren't able to do before because we haven't learned derivatives when we started with limits. So so we are going to review some things from unit 1. Okay, so when we're evaluating limits, especially if we're evaluating at a real number, the first thing we do is direct substitution, right? Because it's a way of information gathering for us. We don't know is it a connected graph, is it a hole, is it an asymptote, and direct substitution gives us that knowledge, that information. So if we plug 3 in for x, what do we get? 1/3, and we can stop, right? There's nothing more to do if we have a real number. Okay, all right. Number 1 here. Let's split it up into 2 parts here because I want to show you the old way and then not old way, but the original way and then the new way that we're going to learn. Okay, so first step, direct substitution. What do we get? Something over 0. 4 minus 14 plus 10. Sorry, what's that? 0. So this tells us that there's a what? Hole, but does the limit exist? Yes, it does, right? So there's something blocking the view of our limit, but we can find the hole, remove it, and reevaluate. So we would go through factoring, right? Multiplies to be 10, adds up to be -7. And then what do we do? Cancel. We see the culprit. We see what's causing the hole. Remove what's causing the hole, and then direct substitution again, and we get -3. Okay, so this is all fine and good, but now we have a different approach to working a limit problem if we get a 0 over 0. So let's copy this problem down again. Okay, direct substitution, same problem. So we get 0 over 0. Okay. Now, if you get 0 over 0, remember, after we learn this L'Hopital's rule, it's not going to replace the first step. Okay, first step is always the first step. Okay, direct substitution, regardless of what method you want to use, is always the first thing to do because you want to gather information. Now, if you get a 0 over 0 or infinity over infinity, we call that indeterminate form. If you get that, you have the freedom to go through what we call L'Hopital's rule. So L'Hopital's rule says this. It says that I can take the derivative of the numerator and the denominator separately, and that will give me a new expression. And if I revalue the new expression, it should take me to the limit. So what's the derivative of the numerator? Denominator?
It's 2x minus 7.
Sorry, 7. Yeah, I didn't write it well. Yeah, 2x minus 7 up top. And the bottom, x minus 2 becomes 1, right? X becomes 1, 2 goes to 0. So now we have a different version of the problem for us to find limit. Okay, so now I'll revalue the limit and we get
-3.
4 minus 7, which is -3. Okay, so now that we have L'Hopital's rule available to us, I think we're going to prefer this over previous factoring methods. So now we just have another option available to us. Okay? But remember, we haven't learned derivatives when we started limits. So that's why we're revisiting this now that we've learned derivatives. But the danger that students experience is they would jump into the L'Hopital's rule before they confirm 0/0. So it's important that you first have to confirm that there's a hole in the graph before you jump into all your steps. So right, so here's the official rule. The limit as x approaches a of f of x over g of x becomes f prime of a over g prime of a. Some of these problems we have to skip because we haven't done the trig part of it because we're saving the trig for the end of the semester. So, but let's just go ahead and try example 2, okay, and see if the steps make sense. So, direct substitution. If you get 0/0, that gives you the green light to do L'Hopital's rule. All right, did we get 0/0?
Yes.
Okay, so let's attempt L'Hopital's rule. Reevaluate denominator. Yes, at 13. Okay, so here's our limit. I don't know if I talked about this before, but AP graders have like a quirk that I think a lot of classrooms don't enforce, and it's something called linkage error. And that is where they are really picky about how they interpret equal signs. So on the AP exam, this only applies on free response. On the free response, if you use equal sign, the way that we use equal signs is we use equal signs to indicate our next step, right? Equals this, then my next step is equal. And, we're not taking any points off for that. But for them, if they see an equal sign, they're looking very carefully on both sides of the equal sign and seeing if they're actually equal to each other. If they're not, it's considered a linkage error, and then they may take off a point. So the way around it for us is, especially with limits, is if you do equal 0/0, technically they're is not equal to 0/0, and so they have a problem with that, and so they may take off a point. So the best way to avoid it is use arrows. If you use arrows, you're not committing to the fact that they're equal. You're just telling the grader, this is my next step. And so I think that's a good strategy, especially on free response. Just be careful of how you use equal signs. And if you just want to show the grader that this is my next step, use arrows to indicate this is my next step. And that way they're not having to, compare both sides and try to take off points. So that's just something, that's a little quirk that the graders are told to do on the AP exam. Now, these problems here, we're going to skip because we're going to come back to trig a little bit later. And also, the L'Hopital's rule doesn't work it's not as efficient if we're dealing with infinity over infinity. If you get infinity over infinity, or if you're approaching infinity, we like to compare degrees. That's just faster than having to go through L'Hopital's rule. So I would say use L'Hopital's rule if you get 0/0. But if you're getting infinity over infinity, you can do L'Hopital's rule. But if you just compare degrees, if you do comparative growth rates, it'll be even faster. Now, one thing to point out is that L'Hopital's rule is not quotient rule, okay? This is not a shortcut for quotient rule. So if I had a function that is, x squared minus 3x over x plus 1, we can't say, oh, I'm going to do L'Hopital's rule for this and just do the derivative. We still have to go through quotient rule because this is asking for the derivative. If it was a fraction and it's asking for the limit and you get 0 over 0, then that is when L'Hopital's rule get applied. But normally we can't just take the derivative of the top and the bottom separately unless it's L'Hopital's rule. If it's meant to be quotient rule, and if you're asked to find the derivative, you still got to go through f prime g minus f g prime all over g squared. We can't say, oh, numerator's derivative, denominator's derivative, and I'm done. So L'Hopital's rule is for limits. Quotient rule for fractions is for derivatives. Okay, just for practice purposes, can we just try just to see our comfort level with L'Hopital's rule? Let's try 1, 2, 4. Yeah, 1, 2, and 4, since we haven't done logs and trig yet. So remember, direct substitution first. If you get 0 over 0, you can do L'Hopital's rule, but if you get a real number, you would just stop, right? There's no need to do L'Hopital's rule if you already have the limit. So, but what if you get 10 over 0? It's undefined. Okay, so you only do L'Hopital's rule if you get 0 over 0. If you get a real number, you stop. There's your answer. If you get a 0 over 0, do L'Hopital's rule. If you get 10 over 0, 8 over 0, you also stop, but you stop because the limit doesn't exist.
Number 2, is that a 38 or a 35?
35. Yeah, it's not very clear. X squared minus 2x minus 35. All right, page 21. So go ahead and try page 21, number 3. You have your volume formula, you have your surface area formula, build the derivatives to begin with. That way you have everything in front of you, and then see if you can start to puzzle, piece the puzzle together. You're just doing a bunch of substitutions and trying to find your way to your the variable you're looking for. Page 21. And as you guys start, I will show the different steps along the way and see if we're on the right track. Okay, everybody okay with the derivative? DSDT and dVdt? Yeah. We're trying to find DSDT, but DSDT, we have the radius for the diameter, but we don't have DRDT. So the way to get a DRDT is we have to use another link here. The dVdt is 25, so we use our dVdt equation to try to figure out what that missing piece is. Once we find DRDT, then we can plug it back into our DSDT equation to find the variable that we're looking for. Okay, any questions with 3? Okay, let's try 4. This is our ladder problem. X squared plus y squared equals z squared. Find your derivative. 6 variables will show up, and you're just trying to figure out what pieces you have to get to your missing variable. Does anybody still need number 3? Yeah, okay. Right, here's number 4, part A.
This is on Tuesday, right?
Yeah.
Are you gonna do a review session that morning?
Yeah.
Okay.
Yeah, Tuesday morning,
And
I'll
we
see you.
start this review what day?
tomorrow. Yeah. But technically, we are kind of already
Yeah.
beginning quiz review, so we're just gonna cycle through
Thank
more
you.
problems tomorrow. Yeah. Part B, area of a triangle. 1/2 base times height, 1/2 x times y. But to find dA dt, what needs to happen on the right side? If we want to find the derivative. How would you find the derivative for 1/2 xy? Product rule, yeah, we can't say 1/2 dx dt times dy dt. These are variables multiplied together. We got to go through product rule for that. Any questions with part A? In this case, because it's the ladder, that ladder is going to stay the same length all the way through. So
For you, when you do the product rule, you would keep the 1/2 on the outside, right?
you can, or you can let the 1/2 be part of the x. Either way, it'll still come out to be the same. Part A, we found the dy dt, the rate of change of the height. What's our unit of measure going to be for dA dt? Area is feet. Area is two-dimensional, right? So feet squared over
Per second.
per second, yeah. But once you have your product rule ready to go, then you're just pulling all the information from part A to get to your answer. And then if you leave your answer in decimal form, that's fine as well. All right, page 22. Back to a cone problem. Okay, does anybody still need the ladder problem? water is being poured into the cup at a rate of 32 pi cubic centimeters per second. What variable is that? We don't see it yet, but positive, right? At the moment when the depth of water is rising at 72 centimeters per second, what is this referring to? DHDT. 72, sorry. Find the radius of the water level. So ultimately trying to find R. But we don't have to do this all in one step. We know we can always get to R from H. So let's just focus on this piece here. So this should kind of help guide what information that we do have. If we want to involve DHDT, then we would like height to produce that for us. So let's do this. Let's find height first, and then the height will lead us to the radius. But DHDT is kind of helping us to know that we would prefer to have the radius to be removed, so that when we find the derivative, DHDT will show up, and then we can use that to help us move forward. Make sure that you know how far you need to go before you jump into the derivative. So a lot of students want to do the derivative a little too soon. And if you see parentheses, multiple variables in the way, you know you're not ready for power rule. I got it all the way down to h equals 2. This is not the variable that I want, but that should be easy to convert, right? If I know the height of the water level is 2, how can I find the radius of the water level? Formula, right? So R is just going to be 2 over 3. Okay, your homework is just to finish the rest of page 22. So I'll send out a reminder today. Tomorrow, I'll give you a quiz review packet, and we're just going to start working through it.
Thank
Every day, guys.
Yeah.
See you tomorrow.
You know, like, how do you think about this? Like, 95 you said.
I'm gonna print out my package tonight, but I was wondering, what was the first homework we did? I didn't have that one saved from there.
Oh,
I don't know if you have it like checked off, if I have or haven't done it.
You did?
I know I didn't do one of them.
oh,
Like, like,
yeah, the, first homework is, page 2 to 3.
yeah, I'll do that.
Okay, thanks.
Charlie, go right now or go to the.
Yeah, advice, yeah, so that's, you know, if someone's looking for you, they'll know where. Thanks.
You write us for, we have like a club meeting.
Are you gonna send Elizabeth like what we?
Okay, I'll tell you. I can talk to them.
Let me see.
Good morning, Delta students, visitors, faculty, and staff. Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please come to a moment of quiet reflection.